Good evening, all. Myself, Dr. Abhishek Tiwari. Today, I am going to present solutions to question number 26 to 23 of A 2018 Metallurgical Engineering question paper. So, this is question number 26, which says the molar free energy in joule per mole of a liquid solution of a binary AB alloy as a function of temperature T and composition X. Mole fraction of P is given by GL T comma X is equal to 1 minus X GA0L plus X GB0L plus RT X ln X plus 1 minus X ln 1 minus X plus 4000 X 1 minus X, where GAL 0, L and Gb 0, L are the molar free energies of pure liquid A and pure liquid B. What is the excess molar free energy GXSL for an alloy with composition X is equal to 0.5 at temperature 1000 Kelvin? In the question, we have been given gas constant R is equal to 8.314 joule per Kelvin per mole. So we can write GXSL is equal to G non-ideal L minus G ideal L. So GXSL can be written as delta H mix, which is equal to omega XA XB. So this is omega XA XB, that is 4000. X is 0.5. Here X is given 0.5. And since X is 0.5, XB is also 0.5. So this comes out to be 1000 joule per mole. So the correct answer is A. Now question number 27. Determine the correctness or otherwise of the following assertion A and the reason R. Assertion A says for a material exhibiting oval creep, a reduction in grain size results in a significant increase in creep rate. And reason R says grain boundaries acts as a barrier to motion of dislocation. So we have to see whether A is correct or not, R is correct or not, and then if R is the correct explanation to A or not. So in this, both A and are correct, and R is not the correct reason for A. So the correct answer is B. I will explain with theory how we arrive at this conclusion. So first, we need to understand the theory behind this question. First, I will explain what is creep. So creep is plastic deformation of materials at elevated temperatures, which is time dependent, which requires stress, and the required temperature is greater than 0.4 Tm, where Tm is the melting point on absolute temperature scale in Kelvin, which is a light limiting factor for several critical high temperature components. Now, if we see the creep strength epsilon versus time curve, we see there are three regions: primary, secondary, and tertiary. So first we will discuss primary or transient creep region. So in this continuously decreasing creep or strain rate is there with time. So that is the slope is decreasing with time. That indicates the creep resistance or strain hardening. Now the secondary creep regime, and this secondary creep regime is the steady state creep region. As we say, the slope is constant. This strain rate is constant. So the creep and strain rate is constant with time, and the plot takes almost a linear shape. And the reason of this is the reason of longest duration. And the constancy of the creep rate is attributed to the balance between strain hardening and recovery. Recovery is a softening mechanism, and this regime determines the creep life of a high temperature component. And this regime region should be as long as possible. Now, we have seen the two particular terms in this strain hardening and recovery. So, first we try to understand what is strain hardening. So, the ductile material becoming harder when plastically deformed as a result of extensive generation of dislocations and straining and crystalline structure. So, this is called strain hardening or work hardening. It's also called work hardening. Now, recovery. So, the stored strain energy is removed by virtue of dislocation motion and enhanced atomic diffusion at elevated temperatures. This results in annihilation or vanishing of dislocations and improved ductility. Depending on the temperature and stress, different deformation mechanisms are activated. Though there are many deformation mechanisms active at all times, usually one mechanism is dominant, which accounts for almost all deformation. So the various mechanisms are: first is bulk diffusion, also called Navarro-Herring creep. Second is grain boundary diffusion, that is Scoville creep. That is glide controlled dislocation creep. In this, dislocations move via glide and climb, and the speed of glide is the dominant factor on strain rate. Now, fourth is climb controlled dislocation creep. So dislocations move via glide and climb, and the speed of climb is the dominant factor on strain rate. Fifth is Harper dot creep. This is a low stress creep mechanism in some pure materials. So at low temperature and low stress, creep is essentially non-existent and all strain is elastic. At low temperature and high stress, material experience plastic deformation rather than creep. At high temperature and low stress, diffusional creep tend to be dominant, while at high temperature and high stress, dislocation creep tends to be dominant. Now, we will discuss Nabarro herring creep. Nabarro herring creep is a mode of deformation of crystalline materials and amorphous materials that occurs at low stresses and held at elevated temperatures in fine-grained materials. In Navarro herring creep, atoms diffuse through the crystals. and the creep rate varies inversely with the square of grain size. So the fine grained materials creep faster than coarser grained ones. Navarro herring creep is solely controlled by diffusional mass transport. This type of creep results from diffusion of vacancies from regions of high chemical potential at grain boundaries subjected to normal tensile stresses to the regions of low chemical potential where average tensile stresses across the grain boundaries are zero. Now, focal creep is a form of diffusion creep, and focal creep is a mechanism for deformation of crystalline solids. Contrasted with other diffusional creep mechanisms, focal creep is similar to Navarro herring creep in that it is dominant at lower stress levels and higher temperatures than creep mechanisms utilizing dislocation glide. Focal creep occurs through the diffusion of atoms in a material along grain boundaries. This mechanism is observed in polycrystals or along the surface in a single crystal, which produces a net flow of material and a sliding of grain boundaries. Navarro herring creep does not have a dependence on grain boundary thickness and has a weaker dependence on grain size. In Navarro herring creep, the strain rate is proportional to d raised to power minus 2 as opposed to d raised to power minus 3 dependence for Powell creep. The lower temperatures favor Powell creep and higher temperatures favor Navarro herring creep because the activation energy for vacancy diffusion within the lattice is typically larger than that along grain boundaries. Thus, lattice diffusion slows down relative to grain boundary diffusion with decreasing temperature. Now, if we compare these two creep, that is Navarro herring creep and Powell creep, the favorable conditions for Navarro herring creep are high temperature, low stress, and small grain size, and the favorable conditions for Powell creep are low stress, fine grain size, and temperature less than those for which Navarro herring creep dominates. In case of Navarro herring creep, vacancy diffusion is through crystal lattice, and in case of Powell creep, the vacancy diffusion is along the grain boundaries. And the values of A, N, and P for strain rate formula ADGB upon KT sigma upon G raised to power N and B upon D raised to power P. So value of A for Navarro herring creep is between 10 to 15, N is 1 and P is 2. And for Powell creep, the values for A are between 30 to 50 and N is 1 and P is 3. Now coming on to the question, first assertion is true as the Powell creep rate is inversely proportional to cube of the grain size, and the Powell creep is more active at lower temperatures when self-diffusion is difficult to occur. The grain boundary controls the diffusion rate as the grain boundaries are high energy regions so can accommodate more strain and diffusion can be readily active. Now coming on to the reason is also true. The grain boundaries act as barrier to dislocation motion, and this is the reason why we get dislocation pileups and strain hardening condition. The answer is though both are correct, we can see that the reason does not explain anything about Powell creep mechanism or rate. The reason is only focused on grain boundaries and dislocations, and these cannot explain the diffusion mechanism or strain rate dependency of creep on grain size. So the correct answer is B. Now, question number 28. Determine the correctness of the following assertion and reason. Assertion A, refractory BCC metals like W and MO are less ductile than FCC metals like Ni and Pt at room temperature. Reason, BCC metals have fewer independent slip systems than FCC metals. So this assertion is correct and reason is false. So the correct answer is D. I will explain you in the later slide why this is so. So assertion, it's true that BCC is less ductile than FCC. The reason lies behind the effective slip occurring in the crystals. BCC has 48 slip systems and FCC has only 12 slip systems. The slip or dislocation motion always occurs in a specified slip systems, and more number of slip systems means more slip occurring. But another criteria while defining the movement is that planes more close packed planes are needed for movement of dislocations. Since FCC have more close packed planes than BCC at low temperatures, the dislocation movement in FCC is more, and hence more plastic deformation, and hence higher ductility. Most of the planes in BCC remains active at low temperatures, and thus very few close packed planes are available for deformation. There are several ways by which distribution move in FCC due to close packed planes, thus adding to its ductility. So reason is false as BCC has 48 slip system while FCC only has 12. If we see BCC actually has more slip systems than FCC, but this reason is incorrect. So A is true and R is false. So the correct answer is D. Now coming on to question number 29. A glass fiber of 5 micron diameter is subjected to a tensile stress of 20 megapascal. The surface energy and elastic modulus of this material are 0.3 joule per meter square and 70 gigapascal respectively. Pick the correct answer based on the information provided above. The glass fiber contains a population of flaws of different lengths. Option A is the fiber will undergo brittle fracture. Option B is the fiber will undergo plastic deformation but not fracture. Option C is fiber will undergo elastic deformation but not fracture. And option D is fiber will undergo buckling. Now, to solve this question, we have to understand Griffith theory, that is half the crack length. So this is the crack, and 2 is the crack length. So A is the half, is equal to 2 into 70 into 10 to the power 9 into 0.3 divided by pi is 22 by 7 into A and raised to power whole raised to power 0.5. From this we get value of A that comes out to be 33.4. So sorry, this is half the crack length actually. So A comes out to be 33.4 into 10 to the power 6, 10 to the power minus 6 meter. So the crack length, that is 2A, comes out to be 66.8 into 10 to the power minus 6 meter. So that is 66.8 micron. But in the question, it is given the fiber diameter is 5 micron, which is less than the crack diameter. So the elastic deform. So obviously the fracture will not occur and elastic deformation will occur. So considering all the options, option C is correct. This says fiber will undergo elastic deformation and not a fracture. Now coming on to question number 30. Two equal and opposite charges plus q and minus q are located as shown in figure above. A surface integral Fi is defined on surface Si of the sphere of radius Ri as follows. Fi is equal to surface integral over surface Si E vector dot n cap ds, where factor E is the electric field and n is the unit normal to the surface integration. And if R1, R2, R3 are in the ratio of 1 is to 2 is to 5, so R1, this is R1, R2, and R3 are in the ratio of 1 is to 2 is to 5. Use Gauss divergence theorem to determine ratio of F1, F2, and F3. So according to the Gauss law, total flux linked with a closed surface is Q by epsilon naught, where Q is the charge enclosed by closed surface. So if we see that F1 related to this sphere is F1 is equal to plus Q by epsilon naught, and F2 is minus Q by epsilon naught. And if we see F3, that is plus Q minus Q divided by epsilon naught. So this will be equal to 0 by epsilon naught. If we see the ratio of F1 is to F2 is to F3, so we can see that this is plus 1 is to minus 1 is to 0. So the correct answer is option C. So thank you for your attention. So this was the part B of GATE 2018 Metallurgical Engineering question paper. So thank you very much for your attention. And so we end this video, and after that we will meet for the next part of this paper.